Hello, everyone. My name is Cohen. I'm speaking to you from Hudson, New York, in the USA. Going to talk today about the MBO culture system. Uh, my talk is vaguely based on several papers, particularly the consensus papers that are existing in our field, fortunately, as well as systematic reviews that are published from time to time about different aspects of the environmental and the MBO culture systems. My talk is about the MBO culture system. As I said, it will talk about culture media, incubators, quality control, environmental conditions, and many other aspects. My associations are listed here, and these are my potential conflicts of interest. My main job is developing AI and robotics in order to develop tools that can be used in the IVF laboratory. I'm the Chief Scientific Officer of Conceivable Life Sciences, which is based in New York City and also has laboratories in Spain, the UK, as well as Mexico. This is a startup company. My other associations are listed here as well. So I'm using the system for this presentation really based on consensus workshops. I'm doing this. I'm doing this because it gives you a really broad overview of all the different topics that are important in the aspects that I will go over. So in IVF, there have been, in the IVF laboratory, fortunately, there have been quite a few workshops aiming at obtaining a consensus between small groups of experts. I've been involved in a few of them. There's, for instance, the Istanbul consensus on the top left here, which is a workshop on MBO assessment. And this particular workshop got together more than 10 years ago, and I think is being revisited. It's called the Istanbul Consensus, and it is about the growth of embryos and how you morphologically assess them. This was a combination of alpha scientists and reproductive medicine experts, as well as a special interest group in embryology experts. The one on the top right is another particularly well-known one called the Vienna Consensus. Also, this was the same group of the same groups that the same professional organization that organized this meeting, ASHRA and Alpha. And this particular consensus was on the development of art laboratory performance indicators, key performance indicators, KPIs. And that meeting was published in about 2017. The one I like to talk about mostly today is the one in the middle, which is the IVF consensus guidelines on IVF culture conditions. And that was the so-called Cairo consensus. And the title of that particular meeting was, there's only one thing that's truly important in an IVF laboratory, everything. And so this particular meeting, the experts here felt that they could not emphasize one single aspect, or even 10 or 20 aspects. They came up with 50, but they basically decided really everything is important. So this is a good paper to read. It's freely available from the RBMO website. It's a great paper to read. And I highly recommend that you look it over. Hopefully you have already looked at it. If not, you can look it over after this particular presentation. This group got together in 2018, and the paper was published in 2020. Although there are 50 consensus points, the reviewers of this paper asked us to come up with a new table to list 20, to make it more concise. And in this 20, basically, there's, of course, data handling and expressing what is important or not. In this case, of course, the chance of every patient having a healthy baby is the most important outcome. It's the outcome that this field is striving for. And of course, that applies also to the IVF laboratory. Guiding and embryo assessment practice should be based on expert or professional body peer-reviewed, published in evidence-based guidelines. This is basically the aim of this meeting. And after that are many different aspects that I will go in the next 20 or 30 slides or so. How you keep culture media, how you keep them safe, how you monitor them, that you have to use manufacturers' recommended storage conditions, that you have to develop standard operating procedures to verify acceptability for receipt and use of all contact materials in accordance with best practice and local regulations. This includes keeping permanent records of certificates and of analysis, lots, batch numbers, that there's commercially manufactured culture medium available. It's really excellent nowadays. It's intended for human art and should be used with adherence to protein supplementation guidelines for manufacturers. That spermatozoa preparation for ICSI should be held at ambient temperature to minimize reactive oxygen species generation. A lot of different points that are discussed in this particular table. I tried to focus on 16. I tried to focus further on the 7 that are highlighted here: temperature, culture media, buffering, pH, sequential or single step media, culture media use and management, laboratory equipment, real-time monitoring of equipment, and incubators. And then I felt that I actually should organize it more specifically within that context. To culture media, whether we should use sequential media or single-step media. You're not familiar with these probably. If you are, sequential media are media that are basically being developed in different steps, looking at the 5-6 days of development that we can imitate in the laboratory of these free living pre-implantation embryos, that there are different conditions in nature in the fallopian tube and later in the uterus, different chemical conditions, and these can be translated in the formulations that are used for these so-called sequential media, and you go from step to step. But there are also single-step media that are very effective, and these have been developed in different ways, which I will discuss with you. And then how do you culture? Do you culture them as a single embryo in a droplet, not with other embryos? Or do you use what's called group culture? Do you think that's beneficial or not? And some people believe that group culture is preferable over single embryo culture. I'll go into that briefly. Then about the different incubators that have been developed. 30, 40 years ago, in the early days of IVF, the incubators that were available were cell tissue culture incubators. They were incubators that were manufactured for the purpose of culturing single cells. And so cell tissue culture actually was the field that, from the IVF lab perspective, was the field that was used by the first embryologist to build on. We had not developed, in 1980, we basically had nothing developed that was specific to IVF. The production of different materials and different tools, and also including incubators, specifically for IVF and human embryo culture, all of that happened after 1980. And particularly in the last 10, 20 years, that field has skyrocketed. And not just in the area of incubators, but in all aspects of the laboratory. Embryo assessment and handling is something I will briefly go over. The temperature, do we need to maintain temperature? And what is the optimal temperature? Buffering and pH, I will address that. And then the monitoring conditions and quality management, quality control of the monitoring conditions. And how should we look at all our instruments in the laboratory? And finally, go over some conclusions. Now, this is the only historical slide I'm going to show you, so don't be worried. It's not going to be a story on the history of the IVF laboratory. There are basically three types of culture media. It's the culture medium, the fluid conditions of the embryo, that of course are very important for embryo development. That's been known for a long, long time. And there are basically three types of culture media. In spite that if you look up commercially available culture medium in IVF, there are dozens and dozens of different types. And it seems like they're all different, but they're not really. They fall into three groups. One that actually is hardly existing anymore is the first one, which are the first culture media that were ever developed at the end of the 19th century, particularly in Germany. And these so-called simple salt solutions were based on blood serum. And the most famous ones were the first two that had been used on embryos until about 1970, 1980. They were used on embryos, and these were Ludwig and Ringer's solutions. And these were effective to some extent, culturing blood cells, culturing muscle cells, culturing cells from different origins. But it turned out that embryos were only maintained for a little bit, for several days and not much longer. And they weren't under the best conditions. But these culture media were very helpful because they taught the early experimental embryologists that conditions weren't great and that other culture media should be developed. And that's indeed what happened from 1970 onwards. And there are basically two types of culture media. The one that I call the back to nature media, meaning these culture media's formulations have been based on natural conditions in the fallopian tube and the uterus, where they are mimicking the reproductive tract. Sequential medium is one form of back to nature medium. And indeed, the first commercial medium that was developed for IVF and came on the market in France in 1984, which was Meneso's B2 medium, Yves Meneso, who's a famous molecular biologist, chemist in the area of experimental embryology. He developed this media, and it was indeed very successful, only available in certain countries. But that was the first commercial media. So how were media made before that? They were made by individual IVF clinics. So the first IVF clinics that came about in the early 1980s, those all had their own laboratory ways of making culture media. And these were mostly back to nature formulations that had been published in the literature and that were imitated by the laboratories and made by embryologists, clinical embryologists, on a usually a bi-weekly basis. So sequential media came much later in the 1990s, developed by David Gardner, famous embryologist from Australia, originally from England, who developed a system arguing that the conditions in the fallopian tube and the uterus are different. And since the embryos are the first few days in the fallopian tube, that you should do a changeover to more uterine-related conditions on day 3 of development. And so this is a biphasic medium, although you could argue there are actually 3 phases, because the fertilization conditions in the first day after egg retrieval and sperm preparation are conducive to the fertilization conditions that are achieved in the fallopian tube. And so that is the back to nature family of culture media. A third family is that it's developed completely different from the other, from the work that's based on natural biology before. And that this was developed in the late 1990s, by a group called the Culture Club. These were famous experimental embryologists in the United States who got together in an unusual way and approached the National Institute of Health and they told them, well, listen, we don't want to apply for regular NIH grants. We really want to have a very heavy long-term commitment by NIH to develop culture media and study culture conditions with the aim to optimize human IVF. Human IVF, by the way, experimental embryology in human IVF is not supported by the government. You can't get a grant and study fertilized human eggs and do a randomized trial in human embryology. That's not been permitted since 1980. I refer to it as the moratorium. However, this particular group of scientists said, well, we won't use human eggs and sperm and embryo, but we're going to do this in several mammalian species and see if we can optimize media in a way. And they used an interesting approach. They said, well, we do not know if natural conditions in the reproductive tract are really important. Are they really so good that it is helpful to translate that to conditions in the laboratory? Or are maybe human zygotes and embryos prone to their own circumstances, and do they prefer things chemically in a certain environment that is not necessarily directly associated with back to nature phenomena? And so they realized that you need about 10, 12 ingredients and maybe more, and that it would be difficult to build all the different combinations of these media, because you would get thousands and thousands of different combinations, and it will take you many, many years to study all these different media and find an optimized system for instance, the mouse embryo. So they came up with a system, and this was proposed by a scientist called John Biggers. John Biggers was leading this culture club, and he used a mathematical approach that is aimed at simplifying multiple origin conditions, and it's called simplex optimization. And he developed a media, he and his colleagues developed a media called simplex optimization medium, or SOM, S-O-M, SOM. But they found out soon that it had to be optimized because potassium had to be added at a different concentration that they had seen from the early range of optimizations. And so the medium was called K-SOM for potassium simplex optimization. And K-SOM became a media for several years. It was very popular, particularly in the bovine industry, and very popular in the mouse laboratories around the world. And it hadn't been used until 4 or 5 years later, now a little bit over 20 years ago, by a small group of clinical embryologists. I was fortunate to be one of them, but the leading scientist in that group was Klaus Wiemer, and we developed a medium that we later called Global, as that it was globally acceptable, not necessarily internationally, but globally acceptable, as it could be used for any conditions of human IVF laboratories. And this global medium is basically derived from K-SOM with small adaptations towards the clinical usage, and became a popular medium, although it competed with sequential medium, which was developed by David Gardner. A sequential medium, a biphasic or triphasic medium that was used by David and promoted very effectively and very successfully. And those two media were competing for about 20 years, and I'll talk about the consequences of that. So which one do embryologists prefer? Do they prefer sequential media or single-step media? And it turns out that if you go to Wikipedia as one way, you could also ask ChatGPT or another AI, and they'll come up mostly with the same answer. Here Wikipedia states single or sequential medium are equally effective for the culture of human embryos to the blaster stage. So in the randomization studies so far, and there have been many, many, many randomization studies published, most of them are underpowered. Most of them are not blinded to embryologists, for instance, not blinded to nurses or doctors during embryo transfer. So most of them haven't been conducted very well. But there are a lot of these randomized studies published. And so if we look at that, and the first one to look at was the last Cochrane report on the systematic review done by Sebastian Mastenbroek's laboratory, Sebastian from Amsterdam, with Yusuf as the first author, and other famous evidence-based medicine scientists in this group, such as Sjoerd Rapping and Monty Cohen van Wely and Van der Veen. These people are very experienced doing this type of work, and they came to the conclusion that although optimum culture medium is important for embryonic development in vitro, and that there has been much controversy about the most appropriate culture medium, there have been numerous studies performed, and I mentioned most of those, but no two studies compared the same culture media, and none of them found any evidence of a difference between the culture media used. And also, I must add, if you look at the way that was done, you can actually see that most studies are not about comparing sequential with simplex optimization, single-step media. Most of them actually were looking at manufacture differences, and those are not that interesting. And so they concluded there is insufficient evidence to support or refuse the use of any specific culture medium. But they did not set out to compare sequential medium with single-step medium. A systematic review published by Laura Yancey and Katerina Rikowski's groups, with the first author being Svan Turris, Yannis Van Turris, and other co-workers, was published in 2016 about Blasis culture using single versus sequential media in clinical IVF. This was a systematic review and meta-analysis of randomized clinical trials. And they concluded that single media had the advantage for extended cultures. There were practical advantages. Of course, you're only using one medium, and blastocyst formation rates appeared to be somewhat higher. There was insufficient evidence to recommend either sequential or single-step media as being superior for the culture of embryos all the way to day 5 and 6, so all the way to blastocyst formation. And they said we need more well-designed trials. A year later, the group from Diamant in Jose Franco's laboratory from Brazil came to a similar conclusion, comparing again sequential versus single-step media. And they concluded that the choice of embryo culture approach, single or sequential, did not affect the ongoing pregnancy rates of patients undergoing ART. After that, there hasn't been much activity making these comparisons, except for a very recent report a few weeks ago, where they looked at IVF culture conditions having an impact on neonatal outcomes. And this was a systematic review and meta-analysis. And they did not find any difference observed for neonatal outcomes according to the embryo culture conditions evaluated in that particular review, and that further research was needed. So in short, the answer is we don't know really what the best one is. And we in the Cairo consensus opinion meeting came to the same guidelines, that we could not conclude that any medium was better than another one. Of course, what we did publish too, and did say in this particular paper, that of course it's important to look at the quality of any given culture medium, and that there could be laboratory or manufacturer differences, and that these media need to be scrutinized and tested with MEA, mouse embryo assay tests, and other forms of quality control testing. That is very important. But you can't argue that a single or sequential medium is more important. There simply is not that conclusion can't be made. Now, another aspect of culture media is, do you culture in one embryo at a time in a droplet, or do you put several embryos in a droplet? That's something that embryologists have been debating for years with very poor studies that were published mostly 20, 30 years ago. And yet a lot of people have very strong opinions whether the embryo should be in a single droplet or be cultured in a group. What we do know is that those that are proponents of culturing in groups, they realize that a lot of embryologists use time-lapse incubators, such as the EmbryoScope. So these are incubators where you have a little dish or a little slide that has tiny little areas where a bit of culture medium is pipetted, and each embryo is kept very strictly at the same spot so that you can have time-lapse imaging done and use that to annotate embryo development. And that gives you a great feedback of differences in, for instance, timing of divisions from one moment to the next, from one important stage to the next stage. And if you do that, you're only culturing one embryo at a time. Otherwise, you would mix embryos, and the computerized system then wouldn't know which embryo it has to follow. And so the single culture people always say, well, if you look at that work and the publications associated with it, and there have been hundreds of publications from TL observations, they argue, well, listen, it's clear that those results are good. And indeed, culture in groups, those results are often good as well. Not always, but the published rates are very good. And the differences are not really clear. Some comparisons were made in studies, but all those studies have in common that they were all there from the 1980s and 1990s. So this really should be revisited. So it's hard to give an answer. It's been known that since the 1960s that mouse embryo group culture is advantageous. In the mouse, if you put all the embryos in one droplet, like 100 microliter, 150 microliter droplet, which is nowadays considered in IVF to be a large droplet. But if you put 20 or 30 embryos in there, they do really well. If you put one embryo in such a large droplet, in such a swimming pool, the mouse embryo looks at this as a swimming pool, so big, it actually doesn't do well at all. And it has significantly lower chances of developing to the blastocyst stage. Now, but that was in the days of large volume droplets. Nowadays, small volume droplets like TL dishes show a dramatic improvement compared to standard droplet culture, old type droplet culture in the mouse. So both systems have sustained positive outcomes in clinical IVF, but you have to watch for droplet size. The small droplet sizes are clearly beneficial for single embryos. And also embryo proximity is important. There have been studies done that if you keep embryos a little bit away from each other, like in 20, 30 microns away, or 100 microns away, they don't do as well as they're sitting right next to each other. So there's a lack of good clinical studies, as I said before, and I think one prefers group culture, but single embryos in small volumes can perform excellent as well. Incubator types. Well, there are many incubators now in the last 10, 20 years. In the early days of IVF, as I said before, there was only those large box, refrigerator size, cell tissue culture incubators. In 2007, Fujiwara published a paper comparing benchtop incubators with one another. They offer improved recovery times after opening compared to the large box incubators. When you open the door, you lose all that gas, you lose a lot of the temperature, and then it takes a while before that incubator recovers. Whereas if you have a small environment and you open the door, and there's probably only embryos in there from one patient, maybe from two patients, you actually replenish the air and you replenish temperature. The temperature comes back up, usually within minutes. So it's a very different type of environment, really specifically made for IVF. So there are small advantages of benchtop incubators, but in this particular study, the technicians were not blinded. And so if they prefer a benchtop, because it's nice to keep the patients separate, blinding is important. If you don't blind investigators in a randomized trial, then there could be some bias. Even if you think there isn't, there's always a chance of bias. Lee in 2010 published an atmospheric oxygen large box. This is also an important point, that the first IVF procedures were often done in with incubators that use atmospheric oxygen instead of physiological oxygen conditions, which in the uterus and fallopian tube are the level of about 5% or lower. So 5% versus 21%, which is atmospheric. And these atmospheric conditions are now known to be not good for the development of human embryos. In actual fact, it's one of the few areas of randomized controlled trials, evidence-based, where the randomized controlled trials have made a clear difference. So reduced oxygen is preferred over atmospheric oxygen. So Lee studied this in 2010 and compared these large boxes with atmospheric oxygen to two-chamber benchtops. And the benchtop incubators offered improved recovery times, but they say that there was no difference in development. There have been sibling zygote studies published, often no difference. A paper that is a little confusing to look at, I'll show you one slide about it, which was published just a few years ago by Castillo and co-workers, which was a survey-based study with Daniel Bryson and Joyce Harper and others. Helen O'Neill was on this paper, and they looked at how clinics were doing, how their results are published by the HFEA in Britain, but were they using different culture media? Were they using a preferred incubator? And they looked at clinic variable level and not cycle embryo variable, and they get considerable limitations to this study. But the estimated mean live birth weight per laboratory was, for instance, in this table, LBR, which is live birth rate, is an average of 0.31. And I looked at the confidence intervals, and it turned out that a small desktop incubator, the MINC, in most of these studies was better than the other systems. There are, of course, other benchtop incubators that are equally good, but they weren't necessarily here. And there was in one particular incubator, the BTF1, which I'm not familiar with, which was considered to have less results, but these differences were not highly significant, and they were survey based, which means some clinics reported and others did not. Embryo assessment and handling. A couple of words about that. During embryo assessment, it's important to keep stasis and to keep conditions as stable as possible. So to maintain proper physical chemical conditions during assessment is important. One has to look at optimal timing and frequency of assessment. With time-lapse, of course, this is quite easily achieved. When you don't have a time-lapse incubator, we have to remember time-lapse incubation is expensive. If you don't have that, how often do you look? Do you look once a day, or do you just put them away at the zygote stage and do you look again 4 days later? And it turns out that all those systems work, and it probably is okay once your culture system is stable and you have tested it and you have results. It's probably okay to leave them for 4 days unattended. That is, you let the system go as long as these incubators are monitored and the gas supply is monitored. The results will be stable. So you have to work quickly when you take embryos from the dishes, when you take the dishes out of the incubators. You'll have to work quickly and you keep assessments maybe outside the incubator to a maximum of 2 minutes. That's what the consensus people came to that conclusion. I think that was a relatively strong argument. We know from micromanipulation that you probably can take them out a bit longer, and then it doesn't matter very much. The time-lapse system allows more detailed and protected assessment, of course, because their embryos do not leave the dishes, and the dishes stay in the incubator. oocyte and embryo handling, you have to manage heat loss in pipettes when you do oocyte retrieval, and that can go very fast. Oocyte collection and needle sets need to be monitored. You need to do maintenance of the temperature close to 37 degrees, limited exposure to light. You have to reduce vibrations, although studies of vibrations are not very clear about that. You have to maintain osmolality. However, osmolality, when it is tested in, for instance, time-lapse incubators, since most of those are dry incubators, not all of them, but most of them are dry incubators, actually osmolality goes up very slowly in the course of the 5 days of culture, apparently without an effect. But they're still well within physiologic conditions, but they significantly go up each day, which is interesting. It means water is lost through the oil layer because embryos are cultured in culture media droplet on the oil, and water is lost during this culture system if there is no humidity. And so that is an interesting phenomenon. Difficult to understand how that works. The pH has to be maintained, and that means you have to monitor pH and or monitor CO2. I would think you have to monitor pH every time you get a new medium batch, and then you can monitor with CO2 because those two are of course linked. Do you need continuous pH monitoring? Maybe. I haven't seen any convincing studies that clearly show that if you continuous monitoring of pH, that is an advantage. So room temperature versus body temperature. Well, in IVF, we're very much convinced that 37 degrees centigrade is the gold standard. And that's probably defendable. It's probably defendable. However, you know, about 30 years ago, almost 30 years ago, Rusty Poole, who is still an IVF lab director in San Antonio, in Texas, in the United States, Rusty Poole published this paper, Simple Approach to ICSI. This was a few years after ICSI was developed. And he and his embryologists were doing ICSI at room temperature. I wasn't all that surprised about that because in mouse embryology, if we do the manipulations related to pipetting and related to micromanipulation outside the incubator and keep the heating stages on, the results aren't as good as when we keep the heating stages off. So in the human, it seems to be different. In the human, embryologists are very paranoid, very worried if the temperature drops below 30 degrees. And I think it's a good point. If they drop below 30 degrees, you do get potential aberrations that may have some effect later on. But even that is not set in stone. So this is what Rusty did, and he has been doing that and is still doing that in his lab. He is also doing egg retrievals at room temperature. Now, when we say room temperature, the dishes come from an incubator. And so do the dishes diminish the temperature? Yes, of course. If they're at a room temperature benchtop in a laminar flow unit with stale air coming out, the flow will reduce the temperature, but it takes about 5, 6, 7 minutes before it approaches 32 degrees or lower. And the procedures in this lab, as he would acknowledge, are pretty fast. So speed is of the essence. If there's a lot of follicular stimulation done and there are a lot of oocytes and a lot of manipulations, then the conditions may go below 30 degrees and that have potential consequences. But if these procedures are done fast, such as ICSI, if that is done fast and only a few eggs per dish, and then another dish is taken once the first 2 or 3 are injected, the difference in results are not remarkable. So, in other words, yes, we need a culture at body temperature. There have been quite a few studies now on reducing the temperature a little bit, a few points of a degree, even one study that compared sibling oocytes coming from the same patient where oocytes are split into two groups, or where zygotes are split into two groups, and the culture is done at 37 degrees or 36 degrees. And apparently that made no difference. But the consensus group from Cairo felt that one should stick at 37 degrees because these lower temperature studies were very subtle and weren't very convincing. They were underpowered. And so that's the conclusion that was drawn. So buffering and pH, maintaining a narrow and stable extracellular pH, PHE that's called, is important for gamete and embryo quality. The ideal optimum is difficult to define. It varies based on media, ingredients, additives such as proteins, single versus sequential media. The variations from 7.20 to 7.35. Remember, pH is a log scale, so that doesn't look like a big difference, but it is. And yet it's within that range, that considerable range, that human IVF embryos thrive. And so where that optimum really is, really much depends on the personal experience of a laboratory, what media they use, what supplementation of proteins they use, and whether they use single or sequential media. The appropriate CO2 levels that are set varies based on elevation and media composition, and also target pH. So if you are at a higher elevation, let's say you have a clinic that's in the Alps and it's 1,000 meters high, then the more CO2 needs to be added to the incubator to maintain that same pH that the clinic has at sea level. So yeah, that's an important thing. I work in 1 week a month. I work in Mexico, and the clinic we work with, that's an experimental laboratory that I work, but the clinic that we work with to do some of our human embryo research, they are at 1,800 meters altitude, and their clinic incubators are set to 6.5 to 7% CO2. What buffers do we use? Heaps or mops? They're both good. And one manufacturer has combined them both in one medium without too much evidence that is beneficial. They're both safe for stabilizing extracellular pH outside the incubator. What happens with prolonged exposure is basically unknown in human IVF. A few remarks on light. Should embryos be exposed to light or not? In the 1970s, there was a paper from Yanagimachi's laboratory in Hawaii, and he showed that in the hamster model, which was one of the models he tested, in the hamster model, light had a particularly detrimental effect on unfertilized hamster oocytes. They would activate, and so the metaphase spindle would make small nuclei resembling pronuclei, but they were really subnuclei. The pronucleus divided into little bits, and it inhibited fertilization, and obviously it inhibited further development. And that was published, I think, a year or two before the birth of Louise Brown, the first IVF baby. And it was taken very seriously. And everybody in the early days of IVF was very paranoid about light. I worked at Bournehall Clinic with Bob Edwards, and he didn't let me use a microscope and turn on the light too high to make pictures. So I wasn't allowed to make pictures. And that was because when you had to make pictures, the exposure time of the embryos to light was particularly prolonged at that period, because digital photography really didn't exist yet. And so microscope light, people were very worried about that for many years. And I think that happened in the next generations of embryologists. They noticed this carefulness about light, realized, of course, that light is not natural in the uterus or the fallopian tube, and are very worried about that. But really nobody knows. Nobody has done, in human IVF, nobody has done extensive research on whether the light is detrimental, white light is detrimental or not. In the case of the hamster, What you could do is use red light or green light, and that would, in the case of red light, 100% suppress the effect of light, and they weren't harmed by that. Whereas green light, you would, about 95% of the oocytes would be protected. But of course, it's very difficult to work in red and green light conditions. It's difficult for humans to work in those conditions in a prolonged environment. So the intensity and duration of light exposure and wavelength should be considered during IVF procedures, but we don't know much about it. The culture conditions are obviously important. Temperature must be tightly controlled. The temperature range is required for each piece of warmed laboratory equipment, needs to be monitored. It may be not that important what exactly the temperature is, more or less 37 degrees, but it needs to be monitored in case you see temperature drift of an instrument, that you can find out before there's a spike in temperature or a drop in temperature. You need to see subtle fluctuations of instruments, particularly incubators, before disaster strikes. A slightly lower temperature of human embryos is much safer than a higher temperature. Human embryos can be cultured at 36 degrees, probably even 35.5, 35 degrees. In the mouse, you can culture embryos safely at 34, 35 degrees instead of 37 degrees. But also in the mouse, if you go to 38, that's still acceptable. You go to 38.2 degrees, there's a complete cliff and drop-off, and the mouse embryos are very unhappy at that temperature or higher temperatures. At 39 degrees, they will never develop to the blastocyst stage. That's in the mouse. We think in the human that it's very much equivalent. Incubators, a few words about incubators. The culture environment needs to be maintained through establishment of set points and tolerances. This is what the consensus meeting decided. They said we need culture environment stability of dish preparation. Don't prepare them 10 minutes or an hour before you do the procedure. Prepare them the day before. Gas supply and control needs to be monitored. There needs to be inline filters to remove any unwanted materials, such as volatile organic compounds or aldehydes. The frequency of door openings needs to be limited. Incubator management, you need to do preventive maintenance and daily quality control procedures. Monitoring conditions and keeping those conditions in logbooks is important. In some countries, this is mandatory. For instance, in the United Kingdom, also the United States and Australia, it's mandatory to keep logbooks of all your instruments and instrument servicing logs, etc. And so do you need to monitor every day? Likely. Do you need to monitor some things weekly? Possible. Or are there monthly logs that are needed? To keep track of that, at least one app has been developed. This is the Reflections app. It's a cloud-based, accessible from any mobile or tablet or PC. It's secure, two-factor encrypted. It tracks any instrument. All you need to do is train that particular app, what kind of instruments you have, and then you can monitor them at different times. If you have real-time monitoring using other vendors that have probes for instance, temperature or pH, you can have an API with Reflections, and you can have then similar reporting. It's very good if you're living in a country where there is active inspection of laboratories, because you can show an inspector quite easily and very quickly your reporting mechanism and your logs of inputting daily and weekly and monthly. So we found in a paper that was published about 5 years ago in 36 labs of about similar size, monitoring environmental conditions and instrument parameters using the same app. We found, this was published by Giles Palmer, we found that there were tremendous differences between these labs. So whereas the labs have somewhat similar outcomes, of a narrow range. There are differences, but they are narrow. The difference in management control and quality control were staggering. Of course, there are similarities. Most of the parameters concerned in the lab had to do with incubators. You see on the left, 50% in blue, 50% of all parameters measured had to do with incubators. Warming services was another large group of 11%. Cryo storage conditions, another large group of 11%. And then smaller groups, checklists were very popular. Yeah, I've done that. Yes, I've done that. No, I haven't done this yet. So that's done often too. That laboratories have somewhat in common, but there's tremendous variation in the approaches. Here's a result of it. Here you can see in blue the measured temperature by an external temperature probe that was put into the incubator and read outside the incubator, and the display temperature in orange, which was the same without opening incubator doors over many hours that this was measured. Yeah, that is an accepted difference, but whether that's important, we really don't know. So the display temperature reads 37 degrees most of the time in most incubators, but maybe those sensors aren't as bad as you think, and maybe they're hidden in the warming cabinet, in the wall of the warming cabinet, and therefore attached to a surface that is less likely to fluctuate compared to the measured temperature, the extra temperature probe that is often used by embryologists to get a measure of quality control. And so we think that, I hear this all the time, I think, well, the temperature of the incubator just reads 37 degrees. When you put it there, every time you look, it looks like 37 degrees. And that seems unrealistic, but maybe that is realistic. And maybe it isn't as bad as we think it is. In conclusion, if you look at what's important and what's maybe not important, on balance, the studies have been done. If we compare atmospheric oxygen with reduced oxygen tension, 5% oxygen is clearly better than atmospheric 20% oxygen. 37 degrees is still the gold standard for temperature. Less than 37 degrees in a prolonged fashion, we do not know. The studies aren't clear. And those people that have described that it's the same between 36 and 37 degrees, they haven't followed on that and are now culturing at 36 degrees. No, they have not. They've gone back to 37. So it seems to be 37 is the gold standard for now. pH measurements are important. Are they important daily or every hour or every minute? That we don't know. But they are important, particularly if you have a new batch of culture media or a new batch of proteins or a new batch of additives to culture media. It's important to do pH measurements or do it at regular intervals, like once weekly. I don't know if it's important to use daily. And CO2 measurements alone is not a good idea, but in combination with pH, CO2 becomes a secondary factor that can be monitored reliably. The use of commercial media has outshined homemade media a long time ago, 20, 30 years ago. Homemade media had this big disadvantage that they showed fluctuating results. It's a very different outfit. If you go to a culture medium laboratory, that's a commercial laboratory, and you visit those, you'll see that the quality control conditions there are extraordinarily stringent. Whereas the people there realize that it's not only for just one patient a day or 5 patients a day, but it could be hundreds a day. And so to keep those standards high, they have very high levels of quality control. So commercial media, in spite of the occasional bad press, commercial media are highly advisable compared to homemade media. Blast cis transfer compared to cleavage states transfer, we didn't talk about that, but on balance, blast cis transfer probably is a preferable system. On balance, humidity versus dry incubation, probably the same. Optimal extracellular pH within a confined range, it's probably the same. Single versus sequential media, probably the same. And freezing all embryos versus fresh transfer and freezing the rest of the embryos, that is probably the same as well. So that's the report. Pretty quickly from the Cairo 2018 consensus meeting. I thank you very much, and I'd like to thank media, Mina Alikani, Charles Palmer, Marianne Svedic in the Cairo Consensus Group with Mohammed Fawzi, and Sharon and David Mortimer. I also like to thank Professors Ricardo Talivi and Brian Dale for their kind invitation. As my previous slide showed, on the bottom right is my email address, jc@embryos.net. You're welcome to address any questions you have. Or maybe this can be managed by the media team and addressed to me in another way. Thank you very much.